In this video, we will see about lenses. First, we'll see about different lenses, different type of lenses. Here you see the convex lenses, and first one is biconvex, and different radius of curvatures are there. That is R1 and R2. And second one, both sides same radius of curvature. That what we call equiconvex lens. Suppose one side the surface is flat surface, nothing but radius of curvature is infinite. That what we call plano-convex lens. And fourth one, that is a concavo-convex lens. That means here you see R1 is convex, R2 is concave. But here radius of curvature R1 is less than R2, nothing but convex is dominating concave radius of curvature R2. That's why this is a concavo-convex lens. Convex nature is dominating here. Other type of lenses is concave lenses. In concave lenses, you see first one biconcave lens. Two different radius of curvatures are there, and second one equiconvex. Both radius of curvatures are same. And third one, it is one side is flat surface, radius of curvature is infinite, and other end radius of curvature is r. This is a plano-concave lens. And same this case is there in the first also. Here this is a concavo-convex lens. Here it is convexo-concave lens. What is the difference? There R1 is less than R2, so convex nature dominates. Here R1 is less than R1 is greater than R2, so R2 less means which radius is less, that dominates. So concave is less, so it dominates concave nature. So it is convexo-concave lens. Now we'll see some important points about lens. And the lens, a line which is drawing perpendicular to lens passing through the center. The center what you call optical center. That line what you call principal axis. There are two focus points for lens. For mirrors only one focus point is there. For concave mirror you get front side. For convex mirror you get back side. But here for lenses we have two focus points. And one front side we get, and other one back side we get. And their center of curvature is equal to 2f, but here it is not like that. Here different values are there. That's why here f and 2f. 2f is not center of curvature. So either side, both sides we get 2f. And the distance between focus and center what we call optic center, that is what we call focal length. Now we'll see sign conventions of the lenses. Just like for mirrors, how we are applying sign conventions. You can measure any values of front side of the mirror, negative. Here also front side of the mirror. Here two types of mirror lenses are there, convex and concave lens. Front side you can take negative, and back side you can take positive. Above principal axis positive and below principal axis negative. Those are the sign conventions. Sign conventions is same as like mirror only. Now we'll see about a real object and virtual object. Suppose if object is there, and from that object the light come out like a diverging rays, that what we call real object. Suppose an image is going to form at somewhere, and we are placing some lens or mirror in the path of the rays, converging rays, and where we are taking object, the back side of the mirror, back side of the lens we are considering. This what we call virtual object. And what is a real image? And the rays are converging and forming at a particular point an image, that what we call real image. And what is virtual image? The rays are diverging, but we are assuming a point which is these all diverging rays are coming from a point or diverging from a point. That point what we call virtual image. Now we'll see some important ray diagrams of lenses. For example, you can take and the line which is passing through center, that what we call principal axis. Suppose if a light ray is passing through the lens parallel to principal axis, that must go through the focus. Suppose here it enters from left side, and that goes through the focus which is on the right side. Why? Because for lenses we have two focus points. And similarly the light ray which is passing through the focus from left side, that goes parallel to the principal axis on right side. Suppose if a light ray is going through the optic center, without any bending or without any deviation, it can go straight. These are the three important points about a ray diagram. Now let's see what is the focal length and focus of lenses. Suppose first you see convex lens and a light ray, or you see object is at infinite, we get a parallel beam of light. From left side you see parallel beam of light is incident on convex lens, that will be converge at a particular point called focus. The distance between this focus point and the center of the lens, that is optic center, what we call focal length. Suppose same thing if you take for concave lens means it is a diverging lens, and these rays, parallel beam of rays are diverging, but to find the focal length, what they are doing, they assume that they extend these diverging rays backwards, they are appear to converge at a particular point, that point what we call focus of a concave lens. The distance between this focus point and optic center of the lens, that what we call focal length here also. In case of mirrors, we are taking focal length of the concave mirror is minus. Why? Because focus is on front side of the mirror, and here also concave lens on focus is front side only, so that is a minus focal length. And for convex, there convex mirror and focus point is back side of the mirror, there positive. Here also convex is here you see where focus we are getting back side of the mirror, back side of the lens we are getting, so this is positive lens. So convex lens is positive lens, concave lens is negative lens. Now see lens equation, that is 1 by f equal to 1 by v minus 1 by u, that also we can call a lens formula. Suppose assume a lens, I assume here convex lens is a principal axis here, principal axis. Assume an object is here, object OJ. So you can take a ray which is going through optic center, so which is going through optic center, you can name that as P, and that goes straight without any deviation, like this. The ray which is going through optic center without any deviation can go. The ray which is going through parallel to principal axis must go through the focus. Focus you can take other side, somewhere here is the focus. You can take somewhere here, focus F. Then it must go through the focus. The ray must go like this. Go through the focus where these two rays are meeting. There you can get image. So their image forms. Here is the image. Name that image as IG. And here object distance, from here to here is object distance represented with u, and this distance is image distance, image to center of the lens optic center. The distance between P and F is focal length F. Suppose compare the triangles here. Suppose if you are comparing these two triangles, this one and this one, according to triangle OJP and triangle, this triangle, that is triangle PIG. So what you can write, OJ by opposite IG is equal to here adjacent by adjacent, that what you can write, OP by their adjacent is IP. We know that what is OP, object distance, which is front side of the lens. Front side of the lens means you have to take minus u. IP is the distance of the image, you can take it as a V. Of course, that is plus only. This you get equation number 1. Now use this triangle. Suppose you can draw a foot of the perpendicular here, a foot of the perpendicular, This you can name it as M, a point on the lens. And using these two small triangles, this triangle and this triangle. So according to triangle MP, this is F, and triangle FIG, triangle FIG. Here also opposite by opposite. What is this? That is MP. This point is M, so we can write MP by this is IG. We already know these two are parallel lines. Here to here height, here to here height, both are same. Here OJ means MP is nothing but OJ only. That you can write as OJ by RG. That you write same. Which we can write adjacent by opposite by opposite. Now adjacent, that is FP by FI or IF, which is equal to FP by IF. We can write this total minus this part. This total is IP minus FP, which is equal to, what is FP? FP nothing but from here to here, that is focal length only. So write as F, that is plus only because we are measuring backside. And what about IP? Here to here, that is of image distance V minus again F. FP nothing but F we get. This is equation number 2. So in equation OJ by IG, here also OJ by IG, both you can make it equal. We get relation. We get relation minus U by V, and this side what we get F by V minus F. Now cross multiply. What do you get? Minus UV plus UF is equal to, and VF here. That VF is in that side. That what you get? Minus UV plus UF minus VF is equal to 0. And both sides you divide with UV and F. If you divide UV and F both sides, what you get? Here minus 1 by F. Here 1 by V. Why? Because U and F get cancelled. Here V and F get cancelled. 1 by U is equal to 0. Keep this U and V this side and bring 1 by F that side. So what you get? 1 by F is equal to 1 by V minus 1 by U you get. This is what lens equation or lens formula. So in mirror what you get, here you get plus, but here you get for lens only difference, that is 1 by F equal to 1 by V minus 1 by U. Now let's see magnification of the image. First we'll see about transverse magnification. Suppose you can take a lens and this is our principal axis. Object is placed here. OJ is the object, height of the object is HO, and image forms here, somewhere here, that is the image formed here. IG is the name of the image, height of the image is HI you can take. And this is the optic center, you can take it as P. This distance is object distance U, and the distance is image distance V we can write. What is a transverse magnification or lateral magnification? So magnification, transverse magnification is height of the image by height of the object. That means here you see opposite by opposite. These two angles are equal. If this is alpha means this is also alpha. Opposite by opposite equal to adjacent by adjacent. Nothing but you can write here. From here to here distance is V. By here distance is U. So actually here object distance is negative, image distance is positive. So transverse magnification we are getting negative only for real image. So in mirror that is minus v by u, but here it is just v by u. Transverse magnification. So now I'll see speed of the object and image in transverse direction. Suppose if object is going up or down like this perpendicular to principal axis, with what velocity image is moving up and down. So that is perpendicular to principal axis, that we'll see here. And using that equation, that is magnification, transverse magnification, we can write here that is height of the image is equal to, our position of the image in vertical direction is equal to mt into height of the object. So if you differentiate both sides with respect to time, dh height of the image by dt, nothing but changing the position of the image by changing time, nothing but velocity of the image is equal to mt for given distance of object distance and image distance, and mt is constant, and d by dt of height of the object. So nothing but this is a velocity of the image perpendicular to principal axis. You can think like a y-axis is equal to mt into, and velocity of the image, velocity image, this is velocity of object perpendicular to principal axis y. Okay. It's going up or down, that depend upon mt only. That is mt is negative, what you say, this going up means that moves down. If mt is positive and this object going up means image also moving up. And what you can write other equation, that velocity of the image in y direction, the more perpendicular direction, is equal to, in place of mt we can write v by u into velocity of the object in y direction. Here what is v and u? Image distance and object distance. This is a velocity of the image perpendicular to principal axis. Nothing but principal axis is along the x-axis is there, then you can take along y direction. This is a velocity of object in y direction perpendicular to principal axis. This is transverse magnification. Transverse magnification, already we derived that what is magnification, transverse magnification, that is height of the image by height of the object, which is equal to v by u. So in other way also we can write this value y, because 1 by f is equal to 1 by v minus 1 by u. From this calculate 1 by u value and put in this equation. What do you get? 1 by u. 1 by u is equal to 1 by v minus 1 by f we get. That is we can write LCM vf f minus v, that we can write in this formula. So from equation 1 and 2, what you get, m transverse is equal to, so here f minus v by, and here f we get, v we get cancelled here. This is another formula for transverse magnification only. Suppose if you want to replace with, here we are replacing with u. Now suppose in place of v, substitute the value which is coming from this. So from this what you get, 1 by v is equal to 1 by v is equal to 1 by f plus 1 by u. That is f u is the LCM, u plus f we get. That we can substitute in place of v. V is equal to f u by u plus f. That is equation number 3. Put in equation 1. Then what do you get from this? M transverse is equal to, in place of v, write this, f u by f plus u. By u is there. So what do you get? F by f plus u. So total what you can write, M transverse is equal to, from that, height of the image by height of the object, which is equal to image distance by object distance. Otherwise from that, in terms of f and v if you want, by f, and in terms of object distance if you want, f by f plus u we can write. This is how you write a transverse magnification or a lateral magnification. We'll see about angular magnification. And in angular magnification, suppose for example, we can take there's a lens and somewhere here object is placed and incident ray, suppose incident ray make an angle theta object, so with the principal axis, and this is a refracted ray which is making here theta image, the angle made by the refracted ray with the principal axis is theta image. So according to definition, angular magnification n theta is equal to, we can write tan of angle of image made with principal axis, angle of the refracted ray made with the principal axis, and tan of theta object, that is angle between incident ray and principal axis. If angles are very small, you can write theta of image by theta of the object. Like this, we can define angular magnification. Simply you can say it is a ratio of angle made by the refracted ray with principal axis and angle made by the incident ray with principal axis. Now see aerial magnification in the image. Suppose you can take a lens, an object is placed here which is in 2 dimensions. This is the area of the object and it forms image here which is having area like this. This is the area of the image. So that means height increases and width also increases. So both height of the object and width of the object both are perpendicular to principal axis. So magnification is same. So we already discussed what is transverse magnification. Transverse magnification MT is equal to height of the image by height of the object, which is equal to V by U. This magnification takes place in 2 directions. That's why what you can write magnification of area M is equal to MA. Otherwise, you can write is equal to square of this. We get MT square, nothing but V square by U square. We can write this is the aerial magnification. How many times height increases? Same number of times width also increases. This is about aerial magnification. Now let's say about longitudinal magnification. Suppose for example you can take a lens and this is the principal axis. If object is placed along the principal axis, length of the object is LO and distance of the first end from the center of the lens, that is P, is U1. Second end is U2 distance. Image forms generally for convex lens, it forms a real image. So inverted image we are getting like this. So different positions, so magnification is different. This is the length of the image. So neither object gives image for distance. So here you get V1 and for object gives neither. That's why you can take here V2. What is longitudinal magnification means? Longitudinal magnification is the length of the image by length of the object. That is nothing but we can write it is minus V2 minus V1 by V2 is less and U2 minus U1. What you can write minus dV by du. Change in image position by change in object position. Suppose if you take formula, that is a lens equation, 1 by F is equal to 1 by V minus 1 by U. If you differentiate this equation both sides with respect to some variable X, here F is constant but U and V are changes. So then what you get? D by dx of F power minus 1 is equal to D by dx of V power minus 1 minus D by dx of U power minus 1. And this equation, after differentiation, we know that f is constant. So differentiation of f is 0, we get. And you see here variable is x and here v, another variable. Different variable means what you can write. Suppose generally you can write here d by dx of y power n is there. N into y power n minus 1, we are applying differentiation for this. Again you should multiply with dy by dx. So constant differentiation 0. Here v power minus 1 is there. In place of n, what you have? Minus 1. So minus 1 into y power minus 1, nothing but here minus v power minus 2 into dv by dx. Again for this, here minus is there. Again in formula you get minus, get cancelled, you get plus v power minus 2, that is not v, u, second case, u power minus 2 into du by dx. Send this to on the side. What do you get? Here you can write dv by v square is equal to du by u square. And what we need? M longitudinal magnification, that you can write m longitudinal is equal to dv by du minus of, so we can write minus here v by u whole square, we get v by u whole square, which is equal to mt square. V by u is a transverse magnification, so we get here mt whole square. Now say speed of the object and image along principal axis of the lens. Suppose this is the lens and object is moving towards or away from the lens, image also moves. So what is the relation between object distance and image distance? That is 1 by v minus 1 by u. Suppose if object position is u, and what is the velocity of the object? Velocity of the object is du by dt. And if image distance is v, what is the velocity of the image? Vi is equal to dv by dt. So differentiate this equation, both sides with respect to time. And this is a constant, you get 0 here. And for this, what you get? Minus v power minus 2 dv by dt. Changing the image position by changing time. Minus, in formula we have minus this, right, plus u power minus 2 du by dt we get. How we are getting means this we can write here. Suppose for example you can write 1 by y d by dx is there. What you can write? Or you can write here d by dx of d by dx of y power n. We can write n into y power n minus 1 into dy by dx we can write using this formula. Here v power minus 1 is there, you get like this. And here this part you can send this side, that is here this total dv by dt, what you can write? Velocity of the image by v square. On sending this side, this minus become plus the here. And du by dt, nothing but velocity of the object. So velocity of the object by u square. So what is the velocity of the image? Velocity of the image is equal to v square by u square into velocity of the object, which is nothing but this is transverse magnification only. So we can write velocity of the image is equal to mt square into velocity of the object. We can write like this. When we can apply this formula, when object is moving along principal axis, means towards the lens or away from the lens, along principal axis or along x-axis, means there already we discussed along y-axis perpendicular to principal axis. So here what you can write the formula, that is velocity of image along x-axis is equal to, that is v by u whole square into velocity of the object along x-axis. Velocity of the image along x-axis is equal to mt square into velocity of the object along x-axis. Like this we can write. One of the method of finding focal length of convex lens is conjugate foci method, that only they call displacement method. So in this method they keep object is fixed, object they keep here, and similarly they keep image also, that is image nothing but a screen also they keep fixed here. Screen is fixed. Screen means where image forms, that means distance between object and screen is fixed, and the distance you can take it as a d, distance between the screen and object, and they took that distance between object and screen must be greater than or at least equal to 4f. Why? Because if you take object distance, image distance, if the distance between those two is less than 4f, it is not possible to get a real image. So when only real image forms, when minimum distance between a real image and object is 4f. So they keep like this. Why? Because they arrange a screen. Screen means you must get real image, then only we can catch on the screen. So they start moving this lens, they keep a lens here at a particular distance, and they start moving the lens from object to screen. At a particular distance of that, what you can take it as object distance u, and here image distance is v. We get a big and clear image, we are getting big and clear inverted image we are getting on the screen. What it mean here, object distance is u, image distance is v. Here big clear image we are getting means, so what you say magnification, the total distance between them d is equal to u plus v. We get one relation. Other one, what is magnification? In this case magnification m is equal to image distance by object distance, we get like this. Now further move this lens, this is the first position of the lens, that is L1 you can take. Further if you move at a particular position, for second position of the lens, we get same object image, we get a small and diminished. Small, now we get image is small and diminished, real inverted image we are getting. It is less than, the size of the image is less than object we are getting now. So in that case a new position is here we get distance u, and here we are getting distance v from here to here. That means what happened, object distance, image distance are interchanged. That's what you call principle of reversibility. Initially object distance is u, image distance is v. Now at a v distance of object distance and image forms at u distance. So in this case of course d is equal to u plus v only here also, but what is magnification? In this case magnification m is equal to u by v. So two different cases. Now that's why magnification first case m1, magnification second case you can take it as m2. So here v by u you get. In this method what happen, you see at the first position object distance and image distance are u and v. Second position object distance, image distance are interchanged, what we call principle of reversibility. So suppose you can take a object is placed at a particular distance, image forms another distance. Suppose if you are interchanging object and screen, then also we are getting clear image, but magnification is different we get. That's what we call principle of reversibility. Here from this what you say, magnification in this displacement method, and what you say, and magnification, if you multiply both magnification m1 into m2 is equal to 1 we get. Why they call displacement method? The keep object and screen is fixed and lens is displaced between them and until they get two clear images. One is a magnified image, other is diminished image. This distance difference, that what we take it as a x. X is the displacement of the lens between two clear positions, two clear images positions. Suppose you can take height of the object is HO. Height of the object is HO. In first case, at the lens is at first position, image height is from here is H1, and second position image height is formed is H2. From this magnification, what do you say? What is M1? M1 is equal to height H1 by object height HO. Second case, M2 is equal to H2 by HO. Magnification we can write as image height by object height. So first case, what is image height H1, and second position of the lens, so what is height of the image, that is H2, but object is same. In both cases height of the object is same. If you multiply these two, what you get 1. From that, what you can write H1 into H2 by H0 square is equal to 1. So what you can write, height of the object is equal to square root of height of the image in first case, height of the image in second case, we can write. From this diagram we can write, here you see this is u and this is x and this is u. So u plus u, 2u plus x equal to d, we can write from this. U is equal to d minus x by 2, we can write. Similarly, and from here to here v, and this part from here to here also v. So what you can write v plus v minus x. See, this is v and this also v. So v plus v minus x. So we can write 2v minus x is equal to d, we can write. From this, what you can write, v is equal to d plus x by 2 we get. We know object distance and image distance. So here from the focal length formula, 1 by f is equal to 1 by v minus 1 by u formula. Substitute these values. 1 by f is equal to, in place of v, what you can write, 2 by d plus x. Minus of minus plus, it become y, because u generally we are taking on front side, means minus. So here plus, what is the value here, 2 by d minus x. We get LCM and calculate 1 by f is equal to, what do you get, d square minus x square here, and there you get 2d minus 2x plus 2d plus 2x we get. So this x terms get cancelled, and what do you get, focal length from this, f is equal to, if you do reciprocal, d square minus x square by 4d we get. D is the distance between the object and screen. X is the difference in the displacement of the lens in two different positions, or how much distance it displaced to form two clear images. This formula will see here. There we get f is equal to d square minus x square by 40. This formula we can write like this also, f is equal to x by m1 minus m2. So what is m1? We know that is image distance by object distance, v by u, and m2 is u by v. If you substitute those values, you get f equal to uv by u minus v. We get focal length formula, 1 by f equal to 1 by v minus 1 by u formula we are getting. So this is about focal length of a lens using conjugate foci method or displacement method. We have different methods, so total 5 methods we are discussing. First one is distance object method. In distance object method, how they calculate focal length? They keep object, a parallel beam of light is incident on the mirror, on the lens, and where it is converges, the distance from the lens they calculate as focal length. This is first one, distance object method. Second one, with the help of formula, that is 1 by f is equal to 1 by v minus 1 by u. This is what we call UV method. With the help of this formula, we can calculate focal length if you know object distance and image distance. Third one, using graph method, UV graph method. Already we discussed that. UV graph method. You know, UV graph is like this. In second quadrant, we are getting like this. With the help of OA and OB, they calculate focal length is equal to AA plus OB by 4. This is third method. And fourth one is 1 by U, 1 by V graph. So how they calculate using graph 1 by U and 1 by V graph. So we already discussed this also. Suppose you can take the graph which is drawn like this. This is 1 by U, 1 by V graph. This is O, A dash and B dash. F is equal to 2 by OA dash plus OB dash using 1 by U, 1 by V graph. This is UV graph. UV graph. This is 1 by U, 1 by V graph we can calculate. Distance object method, UV method, UV graph method, 1 by U, 1 by V graph method. And last one what we discussed, that is conjugate foci method or displacement method. In that formula, what you can write focal length F is equal to using fifth method. This is fourth method. Fifth method, and what you can write F is equal to distance between the screen and object square minus displacement of the lens by 40. Otherwise, using x by m1 minus m2, magnification first position minus magnification in the second position. Like that we can calculate. 5 methods are there. Now we'll see characteristics of image found by convex lens. Different positions of object. Suppose first initially if object is at infinite, and according to the formula 1 by f equal to 1 by v minus 1 by u, from that we get v value as f nothing but focal length. Of course object is in one side left side and image forms on right side, but at focal length it forms. And what is the nature of the image? It is a real inverted, very small point size it forms. That's why extremely diminished they give here. Nature of the image, real inverted diminished. Suppose if object is moving from infinite towards to the mirror, so but beyond 2f is there. Beyond 2f means here image forms between f and 2f. So here also object distance is more when compared to image distance. Due to that what you get, diminished, real, inverted, diminished we get. Third case, if exactly placed at 2f. If object placed at 2f, image also forms at 2f, but other side it forms. So here what is the nature of the image? Same size it forms, magnification is equal to 1, real, inverted we get. Suppose if you bring this object more closer to the lens, that is now in between f and 2f, then what happen according to principle of inversion, that is last time it is beyond 2f means we get f and 2f. Now object is between f and 2f, so we get image beyond 2f. So in this case what happen, object distance is less when compared to image distance, so we get magnified image. So real, inverted, magnified image we get. Suppose if you bring the object near to the focal length. Near to the focal length means principle of reversibility, and infinite means it forms at f. Now object is at f means in image forms at infinite. Highly magnified, real and inverted. And below focal length what happen? Between the lens and focal length. Now here onwards we get virtual image, virtual, erect. Generally virtual images all are erect images only. Magnified image you get on same side of the lens we get. So these characteristics same as concave mirror, but in place of concave mirror, real image forms on same side, virtual image forms backside of the mirror. But in case of lens, real image forms backside and virtual image forms on front side. That only the difference. So remaining all cases, suppose infinite means it forms at f, and at 2f means it also forms at 2f, below 2f means beyond 2f, so at f means infinite. So all the cases are same for concave mirror and convex lens. Now we'll see graphs or UV graph of this convex lens. U always we are taking on front side, so that's why I take negative. And we are getting backside for real image, so take positive for that. So V is positive, which is taken on y-axis is positive, on x-axis object distance is negative. So we get a graph like this, and once U increases means what happened, V value decreases. So we get a graph like this, hyperbola. Suppose if we draw a line which is making 45 with x-axis, we know where it touches, that point where it touches on the graph. At that point, object distance, image distance both are same. We know in case of lens where object distance, image distance are same. That is, you see that a third case, if object is at 2f, image also forms at 2f, same side, same size, real inverted. That means here if the line is cut the graph, UV graph, so where it touches, that point is and one side U is 2f and V also 2f. So what you can write, OA is 2f and OB also 2f. So we can write, we can calculate focal length using UV graph, f equal to OA plus OB by 4, 2f plus 2f by 4, we get f. Same graph is there for concave mirror, but that we get in third quadrant. This is in second quadrant we get. There both U and V are negative. Here U is negative, V is positive. That's why we get like this. Another graph also there, that is 1 by U, 1 by V graph. So this also we get in second quadrant, 1 by U, 1 by V graph. And here OB dash and OA dash distances we know. Using this formula, it is F is equal to 2 by OA dash plus OB dash gives focal length. But because OA dash is 1 by F and OB also 1 by F. So 1 by F plus 1 by F LCM, if you take F by 2 into 2 is there, so get F value. Like this, we can calculate focal length of convex lens using 1 by U, 1 by V graph. And above one is using UV graph. Now we'll see about concave mirror. Like a convex mirror, concave lens this is, and like a convex mirror, it always forms virtual image, and backside there it forms. Here reverse case, this concave lens always forms image on front side of the lens, always virtual, diminished only. It never even get same size of the image also, and always diminished virtual erect images only it can form. There is no different cases, only one case, always erect virtual diminished image on front side of the lens. There in convex mirror what happen, always virtual, erect, diminished. These properties are same, but their image forms back side of the mirror. Here we get front side of the lens. That one is the difference. And the graph there we are getting here, this is the graph of lens, UV graph of the lens. You see U value, you can increase U value, any distance you can take, but it doesn't cross a focal length. So always V is less than U only. So maximum distance of image is that is V is equal to F only. It's focal length of the lens. More than that it is not possible. It never forms a real image or inverted images. It always forms a virtual, erect, diminished image only. This is about characteristics of concave lens, UV graph.